Welcome. In this session on artificial neural networks, we'll explore the vectorization and the first part of differentiation of the terms that we explored in the previous session. So let's recall the Kronecker product. And specifically, let's recall Kronecker-vectorization. And we had, from the previous one, we had a vector, a one form, U, for layer 2. And we can write that as a matrix. We had, from the previous term, and we had a single data vector, and we'll write that as our design matrix. The reason for doing this is that later on, if you want to, you can try generalizing some of these results. For now, we'll just write it this way. So that means that our problem is, given a data vector and a weight matrix, we have some desired results, and we need to solve for this W. So we'll write this so we can solve this as I, the identity Kronecker product with the design matrix times the vectorization of the weight matrix is the vectorization of the linear response matrix. So let's rewrite this term, which is this one form, the data one form that's coming in, times the weight matrix for layer 2. And let's rewrite this as, let's define a block diagonal matrix for layer 2, and we'll define that to be this term, which is the identity Kronecker product with our data. And let's define the weight vector at layer 2 as the vectorization of the weight matrix for layer 2. So what this will end up being is, this will take the vectorization of this what we'll do is we'll stack all the weight vectors for all of the hidden neurons. We'll then define the linear product vector for layer 2 as the vectorization of the responses at layer 2. And now what we have is an equation. So what we want to do is we want to solve the responses equal to the block diagonal of layer 2 times the long concatenated weight vector for layer 2. So it's actually not solve. We want to compute. So let's rewrite that as simply compute. So from this, we can now find this linear product vector with these terms. And the reason we're doing this is that we're going to set it up so that we can do the differentiation well. Then the activation vector for layer 2 will be the transpose of that one form. So that will be the activation of linear product layer 2 neuron 1, activation of linear product layer 2 neuron 2, and if we had more neurons in our hidden layer, we would simply carry this on. So now, let's observe, we will need to differentiate. And we know that. So let's observe that this is a vector function of a vector with a vector argument. That is, the vector argument is this W2, which is the weights that are involved. So what we'll need is a Jacobian. So the derivative of this activation vector for layer 2 with respect, let's take it in steps, of the linear response vector for layer 2, and we'll call that the Jacobian for layer 2 activations, and this is going to be a diagonal matrix. That'll be a diagonal matrix of the activations of the linear products for layer 2, and now let's use J to indicate them. And the reason for this is what we went through in a previous session, and that is the partial derivative of this with respect to u2 is 0. The partial derivative of this function with respect to u1 is 0, and so this will create a diagonal matrix. So the chain rule gives, what that will give us is the partial derivative of the activations for layer 2 with respect to the long weight vector for layer 2 will be this term, which is the partial derivative of the activations of layer 2 with respect to the linear products for layer 2 times the derivative of the linear products for layer 2 with respect to the weights. And this term is that Jacobian that we just wrote, and this will be our D, because we're saying that these u's are d times that w, and when we differentiate u with respect to w, the derivative is this block diagonal matrix for layer 2. So now we have this handles all of layer 2. Now we have to go to layer 1. Now let's take those outputs from layer 2 and provide them to layer 1. That is, now that we've computed these, which we computed as the phis, but we can write them as z's, let's take these and provide them to our output layer. What we need to realize is the output from layer 2 is the input to layer 1. That is, these outputs, and then we always have to append the 1 to handle the bias term, these outputs of these neurons are the inputs to that neuron. So that input is what we'll write as, that'll be a 1 form that's going into layer 1. And this depends on the responses. So we can write that 1 form that goes into layer 1, and we can write that as a function of the layer 2 weights. Let's see why that's true. So these arrows coming in depend on the computations that are happening in these hidden neurons. And these hidden neurons depend on the original data that's coming in and their local weight vectors. So this will have a weight vector, this will have a weight vector, and if we continued, each one of the neurons in that hidden layer would have a different weight vector. And so we can say that the input to layer 1 depends on the weights that are in layer 2. And we can write this as, we can say that that is the one form from layer 2 that depends on those layer 2 weights, and then we append a 1 onto it to account for the bias term in our hyperplane computations. So the layer 1 linear term, which is U1, unlike our case with a single, when this was the only neuron in the computation, this now depends on, it depends on its weights, and it depends on all of the weights of hidden layer 2 gathered together. Now, we'll need to have a property, and so let's consider, or let's recall that if we have a one form times a vector, that could be written as the vector dot a vector, and we could write that also as, we could take this and we can transpose that, and we could take that times the one form transposed into a vector. So there are all these different ways of writing this scalar property, and the reason we'll recall this is that we'll want to use this so that we can avoid differentiating one forms, because we haven't gone through that part of differential calculus. So now what we can also recall, and this goes back to vector calculus, is recall the equivalence of a function, and here we'll say two arguments, with a function of a vector argument. And what we mean is that if we have some big function g that depends on weight vector 1 and weight vector 2, that is similar. So I won't use any equivalence here, but that is similar to some function lower g of some vector that is a stacking of the weight vector 1 and the weight vector 2.